Okay, so today I'm going to talk about something quite different, which is large deviations for dense random graphs. Okay. So this is based primarily on work with Raghuvaradhan. So you can think about the problem as follows: how to count the number of graphs with a given property. Okay. So only consider simple graphs, a finite undirected graph without self-loops or multiple edges. So there are 2 to the n choose 2 graphs on n vertices. So you have n vertices, each edge may be present or absent, so there are 2 to the n choose 2 such graphs. And the question is given a property p, okay? Just an abstract question, given a property p and integer n, roughly how many of these graphs have the property p? Okay, so that's a natural question to ask. So for instance, the property p may be that the number of triangles is bigger than t times n cubed. So you know that in the complete graph there are n choose 3 triangles, which is n cubed over 6 roughly. So n cubed is the proper order of triangles in dense graphs. So dense means the number of edges is like the square of the number of vertices. So if you fix some t and you ask how many of these graphs, of these simple graphs, have bigger than t times n cubed triangles, what is that order? Okay, what is that number up to first order accuracy? To make any progress with this sort of question, one needs to assume some degree of regularity on p. So we may demand that p be continuous with respect to some metric or some such thing. It cannot be a completely arbitrary question. Okay, so the question is what metric and what space that we want to consider. Okay, so is this objective clear? So we are looking at all graphs on n vertices, all simple graphs. So there are 2 to the n choose 2 such graphs, and we are considering number of graphs with some given property. So surprisingly, even this question. So we'll see what's the solution of this. So even this question, which seems very basic, was open until people didn't have any idea how to deal with such questions before this work. Okay. Another motivation from a probabilist's point of view, let G and P be the Erdős-Srény random graph on n vertices. So each edge is present or absent with probability P. And the number of triangles in G and P, we discussed this a little bit in the first lecture. So it's roughly n choose 3 P cubed. Okay. And you ask a conditional question. So what if just by chance the number of triangles turns out to be t times n cubed, where t is something bigger than p cubed over 6? You know that it's roughly p cubed over 6 times n cubed number of triangles. So if t is some fixed number bigger than p cubed over 6 and n is very large, what if this happens? So this is a rare event. And what would the graph look like conditional on this rare event? So this is the goal of large deviations. So you condition on the world, condition on some rare event and ask what does the world look like condition on this rare event. So conditional on this, what does the graph look like? So it has more triangles than you expect. So are they all evenly spread out, or are they clustered in some small region? Okay, so it's not clear what is the, and moreover, what is this probability? Okay, so now we'll make use of a theory of graph limits developed by Laszlo Lovász and various long list of distinguished co-authors. And this is related to some early works of Aldous, Hoover, Kallenberg, and so on in probability theory. So this theory will tell us exactly the question that we asked in the beginning, that what is the metric or what space should we use? What kind of properties should we consider? The properties should be continuous with respect to some metric. Now, what is that? So let me describe in a few slides what this theory is, what the crux of the matter is. So let Gn be a sequence of simple graphs whose number of nodes tends to infinity. Okay, so you have a sequence of graphs whose number of vertices is going to infinity. For every fixed simple graph H, let this quantity denote the number of homomorphisms of H into G. So homomorphism is an edge-preserving map. Okay, so it's a map from the vertex set to the vertex set which preserves edges. So you can roughly think about this as a number of copies of H in G, although it's not exactly that. But it's, let's say if H is a triangle, it's just a small triangle, then this is, I think, 6 times the number of triangles in G, okay? Because the 3 vertices can be thrown into G in 6 different ways. So, okay, and then you normalize it by the maximum possible value of this number to get a homomorphism density, okay? So this is a number between 0 and 1. And it is also can be interpreted as the probability that a random mapping from H into G is a homomorphism. Okay? So think of H as a fixed small graph, a triangle or a square or a K4 or something like this, and G as a large graph. Okay? And then you consider the number of copies and then you divide. So if H is a triangle, this should be like the number of triangles in G divided by n cubed times some constant. Okay? Okay, so is this clear, the definition of homomorphism density? Okay, so now we have this Gn is a sequence of simple graphs. Suppose these homomorphism densities tends to a limit for every H. Okay, so the density of triangles converges to a limit. So you have a sequence of graphs, the density of triangles converges to a limit, the density of squares converges to a limit, and so on. So for every fixed graph, these densities converge to these limits. So suppose for every H, you have a limit. So what Lafosse and Szegedy did is that they defined basically this collection of numbers as a limit of this graph sequence, so in some sense. Okay? So Lafosse and Szegedy proved that there is a natural limit object in this situation. If this happens, then these graphs converge to a limit. There is a limit object in the form of a function f in the script w, where this w is a space of all measurable functions from the unit square into 0, 1, okay, that are symmetric. So it's a simple space. It's just a space of all measurable functions on the unit square taking value in 0, 1 and symmetric, fxy equals fyex. And whenever this happens, that this homomorphism densities converge to limits, okay, you can describe the limit of the graph sequence in the form of a function. Okay. So it's not immediately clear what this is, so let me describe this. Okay, and also they showed that any such function arises as limit of an appropriate graph sequence. So now, given a function f like this, one can define homomorphism densities in that function. Okay, so this is how you define THF. So H is a simple graph on k vertices. You take f xi xj over all ij in this edge set of H, okay, and then product over all this and dx1 to dxk and then this integral. So this is will be called the homomorphism density of H in f, in the function f. So roughly what does it mean? This means that you have this interval 0, 1. You think of each point as a vertex. Okay, it's a continuum of vertices. You think of fxy as a chance of x being connected to y by an edge. Okay, so this is the chance that these x1 to xk that you have chosen, they form a subgraph. They form a subgraph of this continuum graph. And so this is basically like the density of H in this continuum random graph. Okay, so you have this continuum of vertices. You connect any two with probability fxy, and you have this continuum graph, and this is the density of H in that continuum graph, random graph. Okay. So a sequence of graphs Gn is said to converge to this function f if for every H this limit THGN is equal to THF. Okay. And the theorem of Lafosse and Szegedy is that whenever they converge, you can find such a function f. Whenever you have convergence for every H, you have all these numbers TH, you can find an f so that TH is equal to THF for every H. Okay, so therefore this f adequately represents the limit of this graph sequence. Okay, so this f is, it denotes like it's a random graph. Okay, so it's a random graph. Now you have this GNs are deterministic graphs. There is nothing random. So how does how do you correlate these two things? You have this. This seems like a random thing. So the connecting thing, is Samaridy's lemma. I'm going to talk about that later on. So Samaridy's lemma, essentially, it's a fundamental result in graph theory. It says that any dense graph basically looks like a random graph. It looks like little components, and the connections between the components are random. So I'll talk about that. Any questions about this slide? Yes?
Can you realize graphs as these sort of limit objects using a finite graph?
Yeah, so I'm going to talk about that. So yeah, in a couple of slides. So any finite graph can also be realized as a limit object. So if each GN is the same, then also there is a limit. Okay, so I'll come to that.
Excuse me.
Yes.
Is there a natural topology on this space of measurable functions?
Yes, we are coming to that. Yeah. Okay. Any other questions? Yes.
GN can stay finite. It doesn't have to measure.
Well, for now, you think of it as tending to infinity, but it can stay finite. Yes, it can stay finite. Okay, so here's an example. If you take the Erdős-Srény random graph, you go to the random graph domain, you take the Erdős-Srény random graph, you take a fixed realization of sequence of Erdős-Srény random graphs. So P is fixed and n going to infinity. You can prove quite easily that the homomorphism density of H in GNP converges almost surely to P to the number of edges of H. Okay? So for instance, if H is a triangle, it goes to P cubed. On the other hand, if f is a function that's identically equal to P on the unit square, then you have this. Then for every H, TH, f is P to the number of edges in H. So these two things are the same. So according to this Lofas and Szegedy definition, these random graphs, G and P, they converge almost surely to this non-random limit function that is identically equal to P. Okay, so that's a law of large numbers for G and P, for the graph itself. So you can talk about various laws of large numbers for various things associated with G and P. This is a law of large numbers for the full graph, G and P. Okay, it converges to this limit function. Okay, so just to fix ideas. Okay, so the elements of W, remember W was a space of all measurable symmetric functions from the unit square into 0, 1. It's sometimes called graphons or graph limits or various other names. Now, one thing to note is that if you just take a simple graph on n vertices, a finite graph, this can also be represented as a function. It's quite a natural way, okay? So you just take the unit square, divide up into little boxes. So you have n by n, like a chessboard, okay, boxes. And in each box, you define the function to be 1 if there is an edge between vertex I and vertex j in the ijth box, and the function to be 0 in a box if there is no edge, okay? So there's a natural way. You just take the incidence matrix of the graph, and then you make it into a function. That's a function that has all the properties. So the homomorphism densities of each h in f coincides with the homomorphism density of H in this graph Gn. So in that sense, this represents. But it's not the only representation. There's a question of uniqueness, of course. You immediately realize that. So we'll talk about that. Okay? So is this clear how to represent a function, a graph as a function? A very simple notion. So this allows all simple graphs, irrespective of the number of vertices, as represented as elements of a single space. So just think of the analogy that you take finite sets of real numbers. Okay, you can have various finite sets of real numbers of various sizes, but each of them can be viewed as, for instance, a probability measure on the real line. You put mass 1 over n on each number, and you consider that as a probability measure on the real line. So just as any finite set of real numbers can be thought of as a probability measure on the real line, any graph on any number of vertices may be thought of as a function here. Okay. Any questions? So now the question is, so now we have found a space in which we have embedded all graphs. We have embedded all graphs. We have been talking about a notion of convergence of graphs. So it's natural to ask, can we put a topology in this space which topologizes this graph convergence? Okay, so let me go there step by step. So it requires a few steps. First of all, you consider the cut distance. So the cut distance was defined by Friis and Canaan, I think. You take two functions, bounded measurable functions, symmetric on the unit square. You define the cut distance as the supremum of the integral of f minus g on all rectangular sets. Okay. So if you took it on all subsets, all measurable subsets of 0, 1, you would just get the L1 distance between f and g. Okay. But here you are taking supremum over a smaller collection of subsets. You're just considering all rectangular subsets of 0, 1. Measurable rectangles. So S and T are measurable. So I didn't mention that here, but these are measurable subsets. And you take the supremum over all this. Now you introduce an equivalence relation. Okay, that's very important because two graphs are the same if one can be obtained from the other by a relabeling of vertices. Okay. So similarly, you say two functions are the same if one can be obtained from other by a relabeling of the points of 0, 1. So if fxy is g sigma x sigma y for some measure preserving bijection of 0, 1. Okay, so measure preserving bijection means that sigma is a measure preserving map and its inverse exists and is also a measure preserving map. Okay. Okay, so this equivalence relation is very important. Now, you denote by g tilde the closure of this orbit. So you take overall measure preserving bijections, g sigma, and you take the closure of this orbit, g tilde. I think the orbit is automatically closed, but it's a hard theorem to prove. But we don't need that. Now, you denote the quotient space by w tilde. So you take any g, you take this orbit g tilde, you denote this space by w tilde, the space of all orbits. So for finite graphs, it means all finite graphs up to relabeling of vertices. Okay, so you identify two graphs which are the same up to relabeling of vertices, and then you take this quotient space. So that's the analogy here. Now, this cut distance, this cut metric, this is invariant under measure preserving bijections. Okay, so if you apply the same one to both of them, it's invariant. So then you define the cut metric on this quotient space as, what you do basically is that you take two functions f and g and you apply permutations to make them as close as possible. So it's like you take two graphs and you relabel the vertices to make them as similar as possible. Okay, and then you take the distance. So that's a metric space. So this is a cut metric on this quotient space. Okay, so this is a space that is a space of graph limits. Okay, not W. This quotient space with the cut metric is the space of graph limits. Any questions about the definition? Okay, so it's a strange metric, and you might consider, why are we considering this? You might ask, why are we considering this? This strange metric on spaces, and the reason is precisely the following, that is here. So any finite graph G has an orbit G tilde. Okay, so you take a finite graph, you take the function corresponding to that graph, and you take its orbit G tilde. Okay, so any finite graph has a natural embedding into this quotient space. It has a representation in this quotient space. So what these authors proved is that a sequence of graphs Gn converging to a limit f in the sense that we defined in terms of homomorphism densities. Remember that we defined convergence to a function in terms of homomorphism densities. Okay, if dhgn converges to thf for every h. So this convergence happens if and only if these images of Gn in this abstract space converges to f tilde in this cut metric. So this is an if and only if relation. So the cut metric is just the right metric to topologize convergence of homomorphism densities. Okay. Any questions? So this
So this method suggests the fact
So the thing is, this metric is something between the strong and the weak topology. It's weaker than the strong topology, but stronger than the weak topology. The problem with the weak topology, as I'm going to mention later on again, is that the weak topology is good for many things, but it does not make this homomorphism densities continuous. So if you ask about the density of triangles, that's not a continuous function with respect to the weak topology.
No. I mean the weak topology induced by these functions that calculated density.
Oh yeah. So
The weakest.
yeah, exactly. It's that. Yeah. This is that. Yeah. So this is that, and this is a metric that metrizes that. So it's kind of strange, but it is the right choice somehow. This is a metric that metrizes these. Now, it's not only homomorphism densities. There are various interesting things that are continuous with respect to this metric. So there is a survey of Austin and Tao where they talk about things that are continuous with respect to this topology. So there are all kinds of interesting things that are continuous with respect to this topology. Okay, but in particular, subgraph densities. Other questions? Okay, so here is our result, and I'm going to tell you how we prove this. So the first thing is the question that I first asked, that number of graphs with a given property. How do you count that? So it's only about dense graphs, because sparse graphs, the results will be all 0 times n squared. Okay, so it's only about dense graphs, and this can be used beyond Erdős-Srény graphs. So for instance, we have used this for exponential random graphs and other things. So it's a general result about how do you count the number of graphs with a given property. So a property is represented as a Borel subset of this quotient space. So you take a Borel subset of W, and that's your property, okay? And graphs on n vertices having this property is the set of all elements of this A tilde, which are images of graphs on n vertices, okay? So you remember that you have graphs which are embedded as as functions on the unit square. Now these functions are quotiented into a quotient space under modulo measure preserving bijections. So each graph you have an image there in the quotient space. Okay, so all elements of this A tilde which are images of some graph on n vertices, and we're interested in the size of this. Okay, we're interested in the size of this set. Let IU be this entropy-like function, half u log u plus half 1 minus u log 1 minus u. And for any h tilde in this quotient space, you define I h tilde as a double integral of I h xy dx dy, where h is representative element of h tilde. Okay. So a priori it's not clear whether this is well defined, whether this is the same for every element of h tilde, the quotient space, but it is. Okay, so here is a result. This function I is well defined and lower semi-continuous on this space. And if f tilde is a closed subset of this w tilde, the f is a closed subset of w, then you have an upper bound of the lim sup of the size of f, log of fn. So fn is a number of graphs on n vertices having that property. Log of fn divided by n squared has a lim sup. You take the minimum entropy, this entropy on this set. And if u is an open subset, then you have a lim inf. Okay, and if these two things coincide, so for instance, you have a set whose closure and the interior have the same infimum of the entropy, then you get an expression for the limit. Okay, this is how large deviation results are usually stated. Okay, so this is Fn. It means all graphs on n vertices which have this property f, and Un means all graphs on n vertices which have this property u. So each property is encoded as a subset of this abstract space. Okay. Questions? Okay, so next I'll present it in a slightly more probability-friendly fashion as a proper large deviation theorem for Euler-Shriny random graphs. But I wanted to emphasize the fact that the result, as stated in the paper, this theorem you'll not find in the paper, but the result as stated in the paper is only for Euler-Shriny random graphs, but it's really beyond that. It's just counting graphs with a given property. That's what the result is about. It's not just a large deviation result for Euler-Shriny random graphs. Okay. Questions? Okay, so counting graphs is directly related to defining large deviations for Euler-Shriny graphs. So for instance, let's say number of graphs in n vertices satisfying a property P is just 2 to the n choose 2 times the probability that an Euler-Shriny graph G and half satisfies P. So this is one connection, and you can connect it in various other ways. Okay, so this is one simple connection between Euler-Shriny and just counting graphs with a given property. So in the paper with Vardhan, the result is stated as a large deviation principle, and it's equivalent to the graph counting principle. So this large deviation principle is as follows. So you take the Euler-Shriny random graph G and P. It induces a probability distribution which we call P and P on this space through this map G into G tilde. So you take an Euler-Shriny graph, it has a map inside this quotient space. It has an image inside this quotient space. So it induces a probability distribution on this quotient space. As before, we define an entropy function. Now there is a P involved, so it's half U log U over P plus half 1 minus U log 1 minus U over 1 minus P. And you define the entropy of H, this P entropy of H, as just a double integral. And okay, so this is the result. It's a proper large deviation result. So for any closed set, P and P of the closed set log 1 over n squared, its lim sup is bounded by this, and this lim inf is bounded below by this. Okay, so that's a large deviation result in the classical sense. Okay. Yes.
Is it you can put f and u to be I suppose f and u could be very easily containing triangles and stuff like this. But
yeah.
Can you have things on the radius of a large cluster, things which are are these type of things measurable?
So then you have to go deeper into the properties of this cut metric. So what is continuous and what is not. So as I said, there is this long survey article by Austin and Tao where they discuss what is continuous and what is not with respect to this metric. And there are other papers by Lofas and co-authors also. So it's an active area they're trying to figure out as much as they can figure out. Okay, other questions? Okay, so so before going into the method of proof, let me just tell you what's coming later on. This is not just an abstract principle. It can be applied to a very simple problem, simply stated problem, counting these large deviations for number of triangles. So what does an Euler-Shriny graph look like if it has too many triangles? As we'll see, this straightforward-looking large deviation principle gives very surprising results. It gives double phase transitions and all that. So we'll see. It's quite different from various other large deviation things that you may have seen before. So just a bit about the method of proof. If you are considering the weak topology in this space, this principle can be proved by usual techniques that you learn in courses on large deviations. However, this weak topology, as I mentioned, is not very interesting. It does not make subgraph counts continuous. So we cannot work with the weak topology. So we have to develop some new method, and that's one of the interesting points. So I'll describe this technique, how this large deviation principle is proved in the next couple of slides. Okay, the first thing that I have to state is Semerari's lemma. So this was proved around 1975 by Semerari, and it's one of the fundamental tools in graph theory these days. So let G be a simple graph of order n, vertex set V, edge set E. For any two subsets of vertices, let EXY be the number of XY edges of G. So number of edges with one vertex in x and one vertex in y. And rho xy be the edge density. So this number of edges divided by the maximum that you can possibly have. Okay, so you can think of them as disjoint subsets. So x and y are disjoint subsets of vertices, and you take the number of edges between them divided by the maximum possible number, size of x times size of y. Okay, so this is the edge density. This is called the edge density between x and y. Now you take two sets A and B of vertices. You call them epsilon regular. Okay, if the following happens. If for any subset of A and any subset of B which are substantially large, which are not too small, the size of x is at least epsilon times the size of A, and the size of y is at least epsilon times the size of B, they satisfy that the edge density between x and y is approximately equal to the edge density between A and B. Okay? So this is a notion of pseudo-randomness. If you had two sets and you put down edges at random with probability rho, let's say, any two vertices are connected to probability rho, you would expect this. If you take two small subsets in them, then also the proportion of edges between the two small subsets should be approximately rho, right? So if things were perfectly randomly distributed, then you would expect this, that you take two small subsets, the density of edges between them will also be rho. So this says, this is a way of expressing that the edges between A and B are roughly randomly distributed. This is a deterministic way of expressing that. That it's epsilon regular if for all sets of substantial size, not too small, the edge density between x and y is close to the edge density between A and B. Okay? Now, a partition of the vertex set is called an epsilon regular partition if it satisfies the three conditions. First, the size of V0 is pretty small, so it's an exceptional set with bad properties. Everything else is of equal size, okay? So it's not as if something is large and small. Everything else is of equal size. So it's basically dividing into k parts, and there's one little part that you're throwing out. Other than that, you divide into k equal parts. And almost all of these pairs, so there are order k squared pairs of these sets, of these subsets, almost all of them, all but epsilon k squared of them are epsilon regular. So basically, you're dividing the set into blocks, into k blocks, so that most of these blocks have the property that the edges between them are randomly distributed, okay, approximately. So that's an epsilon regular partition. Okay. So here is a lemma. The lemma says that basically, once you have fixed your epsilon, you fix your epsilon to be pretty small, 0.01 or something. Then for every graph with sufficiently large size, you can partition into blocks so that the partitioning is epsilon regular, and the number of blocks will not exceed some given thing depending on epsilon. Okay? So basically, any large graph can be divided into a partition, into blocks, so that the edges between the blocks are approximately randomly distributed. And Samaridy's lemma controls this number of blocks if you give an epsilon. Okay, so you give me an epsilon, I will give you the number of blocks that are needed. Okay, it doesn't depend on the size of the graph. It just depends on epsilon. And there is also a little m here, which says that if you want a large number of blocks, then Samaridy's lemma can also give you that. It's not as if you will get 2 blocks always. So if you want at least 10 blocks, Samaridy's lemma can give you at least 10 blocks. Okay. So this is a remarkable result if you haven't seen it before. And we'll see, if you're seeing it the first time, it seems like a lot of conditions, but we'll see it's very powerful, and in the large deviation principle, it's crucial that it's working this way. Okay, any questions? Okay, so any large graph can be partitioned into blocks so that the connectivities between the blocks are approximately random. Okay, so finishing the proof. So suppose G is a graph of order n with an epsilon regular partition V0 to Vk. Okay? So n is very large, k is fixed, think of it that way. Okay, so now once you have the partition, you have the edge densities between the partitions, between the partition elements, between these blocks, you have edge densities. So you take all these edge densities, you construct a random graph where you put down edges between vertices, you take u in vi and v in vj, you put down an edge between u and v with this probability. Okay? So you try to mimic the behavior of the graph with a random graph. Okay? So you start with a large graph, you do this partition, you know the edge densities between the blocks, and then you reconstruct, you construct a random graph out there where you take these exact same blocks and put down edges with those probabilities, okay, those edge density probabilities. So you take the edge density, if the edge density between two partition elements, two blocks is 0.3, then you put down edges between those blocks with probability 0.3. Now, here is the main thing. What Semmelweis regularity lemma tells you is this new random graph that you're considering, that you constructed. The random graph has a property that it's close to the original graph in the cut metric with high probability. So what this says is that in this random graph that you constructed, the density of triangles is approximately the same as the density of triangles in the original graph. The density of squares is approximately the same as the density of squares in the original graph, and so on. Okay? So the random graph may be completely different on a microscopic scale. If you look at two vertices, two given vertices, is there an edge or not? So there'll be lots of vertices for which there is an edge in the random graph, but there is no edge in the original graph. But if you consider macroscopic quantities like density of triangles or density of squares or other things, they will be roughly the same. So this random graph will be close to your fixed graph G with high probability. Now, let F be the probability density of the law of G and P with respect to the law of G prime. So G prime is a random graph with independent edges, remember that. It's a random graph with independent edges. So it has a probability density with respect to, G and P has a probability density with respect to the law of G prime. Okay? So then you can compute the chance that G and P is close to G. So approximately equals means in this cut metric. What is the chance that G and P is close to G? It's approximately equal to this probability density times the probability that G prime is close to G. Okay? So you have a small region in space. How do you find the chance that a random variable y belongs here? It's approximately the density of y with respect to x times the probability that x belongs here, right? So the chance that G and P belongs to this a small neighborhood of G is close to this probability density of G with respect to G prime times the probability G prime is close to G, but this is 1. You know that this is 1 by Semmelweis regularity lemma. You can prove that this is 1. And so you get Fg. So you can compute this chance. Okay? So this was the goal, to find the probability that G and P belongs to a small neighborhood of a given graph is approximately this. Well, this involves this partition. Okay? Okay, and this is where all these entropy functions come out from. Now, the thing is, this space is compact. So this is a result that needs a proof. This is not obvious. The space is compact. The space of graph limits with this cut metric is compact. It's actually not such an easy result, because you take any sequence of functions, you have to find a convergent subsequence, but these functions are invariant under permutations, so they may become completely wild. You have to prove that you can make them tame, so you can reorganize them so that they become nicer and nicer and go to convergent limits. So there's a tower of Semmelweis lemma. So this is a result of Lofas and Sagiti. Since this is compact, you can divide up the space into small, finite number of little balls. Okay? And then this can be computed by just, with all these, the probabilities in all these little balls. So, and they're vastly different. So the largest one will give you the probability that G and P belongs to a given set A. Okay? So that's the argument. That's how you prove the large deviation principle. That is, you first take the space. You want to compute this probability that G and P belongs to a set A. And divide up A into little balls, and within each little ball, you find out the probability that G and P belongs to this little ball around a fixed graph G by this trick, and Semmelweis lemma. and that gives you the result. Okay, any questions? Okay. So I'll go into applications. Here is one little remark, how to find the conditional distribution. So condition on that GNP belongs to a set F. What is the behavior of GNP? I'll just tell you what it is. It's basically you take this set F and see where the entropy is minimized, and GNP will be close to that set, where the entropy is minimized. So given that you know that GNP belongs to a set, so for instance, given that you know that it has a certain number of triangles, the graph itself will be closed to all graphs in that set with the given number of triangles which minimize the entropy. Okay, so that's a general large deviation conditioning principle. So that's how it works. Okay, very concrete application now. After all this abstract theory, let TNP be the number of triangles in GNP, and the objective is to evaluate this limit. So let's say you have some epsilon bigger than 0, and the chance that TNP is bigger than 1 plus epsilon times the expected value 1 over n squared log. So in the first lecture we saw some results about what the behavior of this thing if p is also going to 0. Okay, if p is going to 0, what is the behavior of this thing? So we proved it's like, or we showed it's like, indicated it's like p squared log 1 over p. But here we are asking a different question. Here p is fixed. P is not going to 0. And we want to evaluate this limit. We want to find this limit as a function of p and epsilon. Okay, fixed epsilon and fixed p, and we want to find this limit. So I was working on this before this work also, and using some other techniques. So I proved with Day that this limit for certain values of p and t, so there is a p and there is a t here, for certain explicit set of values, this limit has an explicit formula. It's just ip60 to the 1/3, where ipu is this function. Okay, so we proved this limit, but it does not cover all values of p and t. So you could prove only for a subset, it's non-trivial subset of positive measure, an explicit subset. We proved this, and we tried hard to prove it elsewhere, and we couldn't. And it turns out that it's not true. So this formula is not true for all values of p and t. Okay, so we will see that. So it seems like a pretty nice, large deviation principle, and you would expect some kind of result like this, to hold everywhere, but it doesn't. So and we still don't know the explicit formula everywhere. We know the limit in some variational form, but we don't know it explicitly everywhere. Any questions? Yes?
Where does this k come from, the n squared?
Oh, the n squared? Well, it's because there are n squared edges. So the probability of any rare event, so each atom in the space has mass 2 to the minus n squared over 2. So rare events are like e to the minus n squared times something. Okay, so here is the result, large deviations for triangles. So recall that W is a space of symmetric measurable functions from 0, 1 squaring to 0, 1. Define a functional TF as you take any f and you take this 1/6 of the triple integral fxy, fyz, fzx. That's basically the triangle density. So, and IPF as just this thing, IPFXY, IP was your entropy function. And you define your phi of PT as the infimum of the entropy over all f satisfying TF bigger than or equal to T. Okay, so you take all functions where this is bigger than T and you minimize your entropy. And here is the result, that this limit is precisely minus phi PT. Okay, so it's just a lucky coincidence that in a certain region you can actually evaluate this infimum. And we still don't know how to evaluate this infimum over arbitrary P and T. Okay. And moreover, this infimum is attained. So there is a function which attains the infimum. Otherwise, it would be pretty strange. Okay, so the function that attains describes the limit behavior of the graph. So the function where or functions where the minimum is attained, they are the limit of, in the limit the GNP. What does GNP behave like if you have this condition? If you condition on this, that is described by the function. So if the minimizer didn't exist, that would be strange, but it does. Okay, but we don't know what it is generally. Yes?
Is there any intuition about how this set looks like?
Which set?
The set where you actually have that thing.
Okay, I'll tell you a bit about that. Okay, here is what I call the replica symmetric phase, drawing inspiration from spin glass terminology. So let hp of t be this function that I showed you before, ip of 60 to the 1/3. Let hp hat be the convex minorant of hp, so the largest convex function lying below hp. If t is a point where these two coincide, then you can explicitly evaluate this. Then phi pt is equal to hpt. So you have this explicit function hp, but it's not convex. So you take a convex minorant, and if p and t are such that these two functions coincide, then you can evaluate. And moreover, for such P and T, the conditional distribution of GNP given this condition is basically, in the limit, it's like Gn 60 to the 1/3. So it's a strange thing that if you have GNP and you condition it to have a little bit more triangles than what you'd expect, but little bit means by a fraction more, okay? Not some smaller order of n. A fraction more, it still looks like an evolutionary graph with a higher P. Okay. Okay. So that's a strange thing. You might expect that asking for a bit more triangles would lead to some clustering. It doesn't. It just, if it's not too much more. Okay. Strange things can happen if you ask for too much more triangles. But if it's a bit more, then it still continues to look like GNP with some different P. So this recovers this earlier result. But we also have as error bound of order n to the -12. So this is impossible by Semirides lemma. In Semirides lemma, there is no rate. You have log star n. Okay, that sort of thing. Okay. And this happens because the because the minimizer, because the function that solves the variational problem in this regime is a constant function. Okay. So the function that solves the variational problem represents the limit behavior of the graph. So if you're minimized at a constant function, then you're converging to Erdős-Rényi. Now here is the more interesting case, replica symmetry breaking. So what the following theorem will show is that given any t, if p is small enough below a threshold, then the conditional distribution of GNP, given that t you have more triangles than you expect, it does not resemble an Erdős-Rényi graph. So we prove that it does not resemble. So in what sense? Let C tilde denote the set of constant functions. So this represents all Erdős-Rényi graphs. So each constant function represents an Erdős-Rényi graph. Okay. Now for each t, there is a p prime small enough and an epsilon bigger than 0, so that if p is less than p prime, you can prove that given that TNP is bigger than Tn cubed, this GNP is away from this set with probability close to 1. So let me tell you this more clearly. So you fix a T, if P is small enough, then given that GNP has more than Tn cubed triangles, you know that the GNP does not look like any Erdős-Rényi graph. It's far away from the set of all Erdős-Rényi graphs. It's just away from there. But we don't know what it looks like. We know it's far away from all Erdős-Rényi graphs. So there is there are regimes where that formula doesn't hold. Okay. Okay, is this clear? Okay, so here's a double phase transition, which is, I don't know an explanation for this. So there is a P0, so that if you choose P less than P0, then there exists two numbers, T prime and T double prime, between P cubed over 6 and 1/6. So 1/6 is the maximum density of triangles. So because, in the complete graph, the number of triangles is n choose 3, which is like n cubed over 6. So the maximum density of triangles is 1/6. And p cubed over 6 is what you would expect in an Erdős-Srény graph. So there are two numbers, t prime and t double prime, so that the replica symmetric picture holds if t belongs to this range or if t belongs to this range. But there is a non-empty subset here where the replica symmetry breaks down. So if you ask, if you fix your p small enough, let's say 0.01, I think 0.01 works. So you fix your p small enough, n is very large. You ask, you take a slightly higher threshold. You ask what is the behavior of the graph given that you have that many triangles. It's Erdős-Srény. You go up more, then it breaks down. It's no longer Erdős-Srény. But if you go up even further, close to the maximum, then the Erdős-Srény behavior comes back. And this is purely computational from the large deviation principle. You solve the variational problem. You show that two regions you have coincidence with the convex minorant, and you get Erdős-Srény behavior. And you show in between that it does not. So the way we prove that you don't get Erdős-Srény is very simple. We just show that there is a non-constant function which dominates all constant functions. But that does not mean that non-constant function is the optimizer. But there is one. So no Erdős-Srény graph can be in the optimizing regime. So the optimizer must be non-constant. Okay. So even with this very simple thing, triangles, you get this interesting phenomenon that you have this double phase transition. As you go up a little, you get Erdős-Srény behavior. As you go up very much further, you again get Erdős-Srény behavior, but in between you don't get. So again, it's all, there's a lot to do because we don't exactly know what the phase transitions are, what the phase transitions look like, what is the optimizer in the regime where it's not Erdős-Srény, what does the graph look like. We don't have anything to say except some asymptotic, some results. So here is one thing. For instance, we proved that if p is very, very small, then the optimizer looks like a clique, which is what you would expect. So you take phi pt, we don't know how to evaluate this, but if you fix t and let p go to 0, then we know what it is. Okay? And we also know that if you take a clique, it's like a rectangle, so it's a small, it's a subset of vertices, everything is connected to everything else, and nothing else outside is connected. So this is a clique, okay, with triangle density t. Then if p is going to 0, then this graph looks like that clique. So basically, if p is very small and t is much larger, then you would expect that given that you have density of triangles t, they're all coming from a clique. But that's a very crude result. So at least it shows what the optimizer might look like. Okay. Lower tails a little bit. So this is not in the paper, but it's in some manuscript. If you look at what happens if the number of triangles is less than what you would expect, and so for a little bit, it continues to look like an Erdős-Srény graph. But as you go down, it looks like something else. So for instance, this is one result. So this limit, we don't know what this is. But as u tends to 0, it goes to this, where chi h is a chromatic number. And this is related to this Erdős-Stone theorem, which I wouldn't go into. But what it tells you is the following, that if you condition on the event that t, the homomorphism density is very small or close to 0, then the graph looks like a complete equipartite graph. So for instance, if you're saying that number of triangles is very small, with high probability it will be a bipartite graph of two equal sizes, almost equal sizes things, and bipartite. And generally it'll be equipartite. So this sort of result you can prove. So in this case you can, but again, for fixed u, we don't know how to evaluate. I mean, formally there is an expression, there is a variational problem, but we don't know how to solve it. Again, here also the thing is, if this is just a little bit below the expected value, the graph continues to look like an Erdős-Srény graph. Some applications. So exponential random graph models, these are popular in the social network literature, or in statistics, some parts of statistics also. so these things could not be tackled mathematically. So there were lots of papers by social scientists and statisticians and theoretical physicists, but no rigorous results. Now, using this large deviation principle, these models, several of these could be completely analyzed in the sense that we got all the expressions, but it's still a long way to go because we cannot solve the variational problem. So this is joint work with Percy Diaconis. So this confirms some predictions from this non-rigorous literature about phase transition. So there are very interesting phase transitions in these models. There are jumps and so on, and these things you can do. So what you do is, these are not error Shreni graphs, but as I just said, the large deviation principle has nothing to do with error Shreni graphs. It's just a counting principle for graphs, and you can use that to do this. There are many open questions, even for this simple problem. So what is the set of optimal solutions? One interesting question is the optimizer unique up to permutations? We don't know that. Is it possible to compute a non-trivial solution somewhere where it's not a constant solution? Is it even possible to do it numerically? We don't know. But I'm not an expert in that. Neither is Raghu. So, but we don't know how to numerically evaluate these optimizers. What is this characterization of the replica symmetric phase? What is the phase boundary and all that? So I should mention here that there is some work on that recently by Charles Radin and co-authors. And lastly, what in the sparse case? So in the sparse case where P is going to 0, we don't know how to do large deviations. We can do concentration inequalities, upper lower bounds, but some of it, but we cannot evaluate, do large deviation principles. Okay, and finally, here is some acknowledgement. Dembo introduced me to the problem in 2005, and there was some old manuscript where there was a partial solution by a different method for subgraphs which do not have loops, but it was not published. Okay, so that's all.
Are there any questions? Comments, remarks?
Okay,
No,
I want to say that it's a very, very interesting talk and a lot of ideas, but I must say that idea of continuous and measurable graphs also developed in St. Petersburg in my paper, paper with my students, and it gives you a link between this problem and random matrices, and help to solve all the problem about existence of invariant measures on the countable universal triangle-free graphs. And this is very close to probably to laws, completely independent.
Yeah, I'll certainly take a look at that.
Thanks. Any more remarks? Well, if not, then there is some, before thanking Sourav for the whole course, there is yet another announcement. Is there? No? Okay. Okay, if not, let us thank Sourav.